Okay, so I was asked in chapter 10 how the lines, when you actually go to draw, like the picture, when we're doing some of those examples of um, showing that it's talking about the direction in which the data is spread out. So the way that you know that those always intersect at the origin, or rather, don't even think about it like that. So the thing is that the lines in question that you get come from those associated vectors. You're treating those vectors like points, so they're necessarily going to be lines passing through the origin because you to draw those lines, you are saying I'm drawing the line from the origin to the point associated with that vector. So you're thinking of the vector like u1. If you look like on so if you look at the picture on like page 4 of chapter 10, so on page 4, chapter 10, you have this matrix. Those vectors, to draw those two lines, U1 and U2, you're saying that those are the vectors associated to the first column of in sigma, or sorry, the first column in U, and the second column in U is U2. So you're just to draw those vectors in, you are literally just saying it's the line from the origin to the point associated with that vector. So yeah, they're always guaranteed to go through the origin like that. So that's why that is. That's why they always intersect at the origin. And yes, that's always going to be true in that way. Um, Problem 13.11. Possible partitions besides 3. Can you explain linear combination concept for two Fiedler vectors? Oh, so I assume that this is the one. Um, Let me have a look at which one this is. I think this is probably the one that has the uh, two-dimensional subspace. Um, let's see here. 13, 11. Yeah, okay. All right. So, okay. So your the first part asks to write down the Laplacian matrix. That's pretty standard. Then it says Fiedler vector span two-dimensional subspace. That's true. Analyze all possible partitions which result. So if you this is done in one of the examples, but it's one of the examples I didn't cover in my lecture on it. So let me see if I can find where this is actually done. So uh, it's the square. So it's example 13.7. So so for chapter 13, number 11, look at this is really for part B. Look at example 13.7 on page 21 of chapter 13. So if you've already had a look at that, just to go through that since it's easier than drawing some of this stuff. So the example in question was a square. I think it's labeled like this, 1, 2, 3, 4. So the example in question is a square. So the example that you have in 13.11, instead of being a square, it's a pentagon. And so in this example, when you write out the Laplacian matrix and find the eigenvalues, you have an eigenvalue 2 of multiplicity 2. And so you get a two-dimensional subspace out of this. And so you can find the eigenvectors that span that two-dimensional subspace. So those are listed on page 22. I should say, so this is page 21 and 22 in chapter 13. So yeah, so you get an eigenvalue, and for this one, like I said, I don't have number 11 worked out, but a similar thing is going to happen. You're going to have an eigenvalue of multiplicity 2, and so yeah, you get your Fiedler subspace is going to be spanned by two vectors, and what happens here is that there's choices that are introduced. So the example that is gone through in this on page 22 does it for the square. You have very, very similar thing happening for the pentagon, basically. But you're going to have 5 slots in those vectors. So you see at the bottom of page 22, it says any linear combination using non-zero multiples of both vectors will lead to a Fiedler vector of one of those forms. So this is basically just going through these possibilities of signs here for the linear combination. And so those give 2 different partitions. So there's 6 total partitions because just exhaustively going through to see what happens in each of the slots. So basically using the first vector, as it says, then vertices 1 and 3 are separate, but depending on what you do with vertices 2 and 4, you could get a list of partitions. So you can do the same thing. So the way that you're basically, when you have a 2-dimensional subspace, you have 2 of these vectors. I'm just going to call them like V1 and V2. So this is a spanning set for that Fiedler space. So in order to try to exhaustively list out all the possible partitions, you could consider just looking at vectors that are a constant multiple of V1. So that's what it means when you're only using V1. You could look at vectors that are a constant multiple of V2. And then you could look at, vectors that are generic and that they're some linear combination of these. But that's what is being done here in this particular example. So I don't want to give too much away other than to just say that if you carry out the analysis that is done on page 21 and 22 for this picture and apply that to I can't remember if this was the actual numbering or not of the one in number 11, but it looks like this. So if you apply that same reasoning to this graph, it's basically the same thing. It's just remember, your vector slots, you have 5 slots instead. So it's a very similar thing though. So if you just go look at this example line by line on page 21 and 22, and you can basically say the same thing. You have an extra slot here instead. Okay. So that's when it says be methodical, it just means go through exhaustively those cases. The numbers are pretty complicated. Oh, I don't know what the actual. So for those of you that have actually, off the top of my head, I can't remember what the. So for those of you that have actually written out the Laplacian matrix, what are the eigenvalues in number 11? I don't know, just looking at it. I mean, like that doesn't really. So it doesn't really matter that much. Once you found the vectors, I mean, the numbers in question in that example are, I mean, they're not super nice. What were the entries? Yeah, I mean the entries in question were, like either plus or minus 0.7071. So regardless of what the actual eigenvalues are, you find those eigenvectors, and yeah, I mean, maybe there's, like I said, I don't know off the top of my head what the associated eigenvectors are, but remember you can scale them if you want. You don't have to use them as given. But yeah, definitely have a look at that. Have a look at that example. And furthermore, any of these graph theory questions about using the Fiedler method, you can have a look. you can have a look at any. So there's like a list of examples that are done under the heading is more and trickier examples, and there's a list. I listed this out in that lecture, but there's a list that basically says what each example accomplishes. So the first one in under that chapter heading is it's an example of using the Fiedler method when one of the entries in the Fiedler vector is 0, so you have to make a choice. But so proceeding from there, it gives an example of every single one of those properties that that can happen. So let me go back for a second. There's so this list I'm talking about is on page 16. So on page 16 in chapter 13, there is a list of properties. So this list of properties is a list of properties that the following examples have. So the first one they do, the bow tie example, there's a 0 in the Fiedler vector. The example after that, repeated values in the Fiedler vector might yield choices. So that's basically you have the option of, while technically, right, the like unmodified Fiedler method is you partition the graph by positive and negative. It turns out that sometimes you can actually get a better partition by, instead of just doing positive and negative, you pick some other value and split them. So maybe you will have some small positive values grouped with the negative values, and that will lead to a more balanced graph. But anyway, so that's one example. And then so one is you might choose the K partition as the next one. So you could think about partitioning into more than 2 sets. So you could partition into 3 or 4 sets. The eigenspace corresponding to the Fiedler value has dimension greater than 1. That's this example. That's that square. And so anyway, this is just a slightly modified form of that example. I've literally just added, a single vertex with the usual connections. Let's see here. That's what I get. So then we use the second and third column for the Fiedler vectors. Oh, I see. Well, I mean, you would use your Fiedler vectors would be whatever vectors are associated to the repeating eigenvalue. So yeah, I mean, like if in your list the eigenvalue that repeats is in your list of eigenvalues from smallest to largest is, the second and third, then yeah, you'd use the second and third. Those would be the Fiedler vectors, yeah. Let's see. 8.3. So 8.3, let me remember. So for 8.3, you actually might want to have a look at chapter 7. Because remember that all the PageRank application stuff, is really just an application of Markov chain stuff, and all the stuff we did for regular matrices, which was technically chapter 7 stuff. So for 8.3, really, this is framed as a PageRank problem, but this is actually kind of asking you for some like specific examples of non-regular matrices and why this convergence is a problem. So you can look in chapter 7, and you will see at least one example from chapter 7 of a non-regular matrix where you don't get this X star convergence, and you could use that example as to draw or to come up with a sample internet that solves that. Similar thing for part B. I mean, it gives you a hint in part B. It says, can you design an internet where some of the pages will end up with page rank of 0? So think about how you would do that, and that pretty much gives you the example. But if you it's been a while since we did that stuff. So if you need to refresh your memory, look at chapter 7 stuff. So chapter 7 will have explicit examples of why you needed T being a regular matrix to get. So remember, the way that the PageRank stuff works is when you have a regular matrix T, there was this theorem that we covered in chapter 7 that said that you got this convergence, and the thing that it converged to, the steady state vector, was the eigenvector corresponding to the lambda equals 1 eigenvalue. So you needed regularity there, because without it, you don't have that convergence, and so you end up with, in the A part of this 8.3 exercise, you don't get the convergence at all, so you can't do the analysis that you even need to do for PageRank. Let's see here. Chapter 8, number 2. So the question is, so you're saying, does the PageRank matrix always have to have, does it always have to be regular? So I'll defer on that question, but you should think about what causes, if there's a disparity between your answers to A and B, you should think about what I know that that's part C, but yeah, just looking at it, I see. Well, I mean, yeah, okay, I see what the issue is. I might come back to that in a second if you have more questions about it. But 11.3, I'm having trouble getting my image to show after removing singular values. So let me. So 11.3. Oh yeah, okay. So this is the one you're loading in. So there's a chunk of, let's see here. There's a chunk of MATLAB code right before this, which I'm sure you've already had a look at if you're loading it in into MATLAB with mread, but if it's not displaying at all, then I would say there's some issue with when you create the approximation matrix, the matrix when you've tossed out the however many columns associated with say the last last 100 singular values or something. I'd say if it's not displaying, there's probably some issue with that matrix. So you should just make sure that the matrix that you're telling it to display the image for is of the right size and is being filled out correctly by what you're doing. So I would just go, if you're looking at this chunk of MATLAB code from like pages 10 to 12, when you're doing that, I would just make sure that when you are using these commands that the syntax is matches up 1-to-1 with this stuff, because this for just simply for doing the SVD, like if all that's done correctly, then literally just copy pasting this block should display the image no problem. So if it's not, then something's going on with like I said, that matrix that you're your forming is like either not the right size or something. Um, it just displays one image. Oh, I see. Well, okay. I mean, if you want to, fine. So if you want it to display like, are you saying you want it to display like all the parts at once? That's fine. So that's like if you wanted to, if you wanted it to generate displays for parts like D, E, and F, and I guess G, um, all at the same time. Um, that's fine. You can actually just use what's a MATLAB command that will get that done. You could yeah, I mean, okay, so like Olivia said, you can either you can either just paste it in individually, or yeah, you can't. I was gonna say hold on doesn't work for this because it displays differently. There may be off the top of my head, I don't know of a MATLAB command that like universally works for like display output. There may be one though. So if you look at the like MATLAB documentation for like MShow, I can look at that real quick. Let's see here. Yeah, it seems like you can display multiple images with MShow. Yep. So, oh, okay. So here. I'll post it into the here. Yeah, hold on definitely doesn't work. But so the link I just posted, I think fixes the issue that you're having. Let's see if I missed anything. I don't want to tell you if your example works. You should think about why it works or why it doesn't. But I will say that you don't have to for your sample internet. You don't have to use anything super complicated. You can use the simplest thing that works. Um, so it's okay if your internet is very small. Let's see here. I don't know why the concurrent viewers is not working on my stream count. I don't know what's up with that, but anyway. So let's see. Example 5, chapter 12, part C. Let's see here. Or maybe that's exercise 5, I guess. Yeah, exercise 5, chapter 12, part C. Okay. Chapter 12, exercise 5, part C. Oh, so so the fact that you're so here's the way that this works. So yeah, that's definitely very close to zero. That's not a problem. Although if you were being so in general, let's say that something yours looks like it's very close to zero, but in general with these things, one of the issues you get uh, with all these computations is that you know how like black and white coloring works, so that if you took something that was supposed to be say white and you made it slightly gray, then apparently in the image that looks that can have like it can be like an off-putting look. It could look maybe not as close as it actually is. That's the only issue that you have to worry about when you and of course I went over examples when we did this of potentially you have to rescale. You can rescale them, or you can there's another method you can use to deal with when you potentially come up with negative values instead of just having values that are strictly between 0 and 1. But yeah, no, that's not a problem. Um, yeah, so let me go back to chapter 8, number 2. Yeah, so the comment was that is that it's not a regular matrix because 3 and 5 have no ways of getting to them, so there won't be a one eigenvalue. So basically, the the point is like if you look at which pages can be reached, right? This is a way of kind of backwards thinking to think about whether or not you end up with a regular matrix that describes the situation. So basically, and remember, when we're doing the PageRank thing, there's the split between happenings, the 85%, 15%. But the point is that basically, just from some of these diagrams, you can tell when there's going to be an issue. Um, although um, although in well there's yeah, so typically you end up with a t that is regular when you um, when you do this. So unless you actually go out of your way to seek out a t that's not regular, then that's what you get usually. So it should typically be a regular transition matrix. Um, and if you want to see like why this is, you can look at uh, um, you can look at it's the very first example it's done in this section. So 8.1 gives an example of a sample internet that shows what happens when it goes correctly, and why in that example it's definitely a regular transition matrix. So this one in this example in 8.2, just looking at it, I think that's going to be regular. If you're using the normal like PageRank method, like so, the reason why you get non-regularity in exercise 3 is because you change the way that the PageRank works. So basically, so in this case, in 8.2, I believe, I think the matrix in question is going to be regular, although it could be wrong. It's hard just looking at it. Like I said, I might come back and do that if I have time here in a little bit. No, you won't. So there's no way to like scale the eigenvalue really. It should just come out as one. You can scale the eigenvectors, you can't scale the eigenvalues. Yeah. So if it is a regular matrix, then it should have 1 as an eigenvalue. 12.5, which have I mentioned that one yet? Oh. Well, what about 12.5? So I believe that nothing nothing too crazy is going on in 12.5. In terms of what we did when we went over this in the character recognition chapter 12 lecture. So yeah, it's so remember basically the intuitive idea, right, is you form a character basis for the letters, and then you're comparing the unknown characters to your result from using the character basis, right? So part A of 12.5 you can just do directly. You just literally, 1 is white, 0.5 is gray, and 0 is black. So you can, that's no problem having those matrices. So then categorizing, so remember how, I guess the most important thing I should say from chapter 12, and I'm pretty sure this is covered in the MATLAB part. So the most important thing here is the reshape command. So the reshape command is the thing that you can use to unroll matrices into the vectors, because remember that the way that we do this comparison with character recognition is we unroll the matrices in question into vectors, and then we compare by looking at the distance between the vectors. So once you have the reshape command, then it's just a matter of following the process for comparison that was outlined in this chapter 12 stuff. Chapter 12 is like a fairly there's a lot of examples here, but there's actually not a whole lot in chapter 12, which is nice because the chapter 12 stuff is pretty interesting in terms of recognizing characters and stuff. A lot of nice examples. So the 8 number 3 definitely won't be regular, because like you noticed, like if it's regular, then you automatically get the convergence. So that thing in chapter 8 number 3 part A, that can't happen for a regular transition matrix. Chapter 14, exercise 10. How can we find the next 3 bits of the key if the period is way bigger than what you... Okay, so so this is the last chapter. Let's see, exercise 10. Well, so the point is that you have some amount of the key. You want to find the next bit of it. So how could you do this possibly? This is a recursively defined key. And so the way that this works is if you can figure out chunks of the key, since it's recursively defined, you can generate the rest of it. You just need to know enough. You need to be able to, if you find the correct recursion relation, then you can generate the whole key from, some initial set of bits. So that's how you don't need to know like the whole period of the key. You can actually just know a little bit of it, so long as you can find the correct recursion relation, which in this case you're doing with refined brute force. So remember, all refined brute force is it's like the brute force method, but you don't have to get started until you found that M matrix that has the right determinant. So basically, for refined brute force, it's brute force, except you have that extra theorem that tells you there's no need to even check the way that you did. You can actually just compute the determinants until you're happy, and then you can solve the one that, so you're looking, it even tells you here, it says look for determinant 1 followed by at least 3 determinants that are 0 to do this. So once you've found that matrix big M, you can solve the resulting mod 2 matrix equation for that vector of C's, and that vector of C's gives you the recursion relation, and that lets you generate everything. So that's how to do it. value for data compression that's greater than 1. Do you mean as far as the percentage of the image quality? So I mean that if what you're talking about is what we're calling the image quality, that the way that that's defined. So let's look at chapter 11, image compression, image quality. So the way that image quality is defined, if this is what you're talking about, is it's the sum of the squares of however many singular values you kept divided by the sum of the squares of the total number of singular values. So that has to be 1 or less. Definitely can't be bigger than 1. Just because the way that it's defined, if you kept everything, that would be 100% image quality, and that would be exactly the sum of all the squares of the singular values divided by the sum of all the squares of the singular values. So it definitely can't be bigger than 1. So just I would say first thing is to check to make sure that your syntax is right, and that you're not you're not accidentally dividing by not enough singular values, or the sum of the squares of singular values. That's what I would say. So check that. Compression ratio. So that's so that is fine. That is so whether or not you've saved space with the compression ratio is so you have saved space so long as if you look at the value of the compression ratio, so it's 2kn over n squared. And so as long as the 2nk is less than n squared, or k is less than n over 2, you've saved space. So that is, you've always saved some space if you are tossing some singular values. So the compression ratio should also should never be greater than 100%. That should never be greater than 100%. That's going to be some percentage between 0 and 100. So 0% compression ratio is you didn't toss out anything. So you saved no space, and tossing out everything would be 100%. So no, it should still be between 0 and 100, or 0 and 1. So again, I would just check the I would check your syntax to make sure that what the actual quantity that you get, because this is your compression ratio is, because I mean k is just the number that you're tossing out, right? So what am I looking at here? Oh yeah. So okay. Wait. So yeah, if you're n is, you have an n by n image, so to store everything you'd need n squared. And then so if you are if all you're saving are the k vectors, so associated to k singular values, then the total number you have to save is 2kn. I see. Yeah. Yeah, so I mean, no, so it's possible that you don't. That's right. It is. Now that I look at it, I guess it is possible that you don't save space. Yeah. So it is. I forgot about that. So there's this extra factor of 2. So you have. Yeah. Yeah. So you're only saving space in the event that the k that you are tossing, or the k that you're keeping, is less than n over 2. And so in the event that you're not saving space, well then you're actually hurting yourself. So your compression ratio would um, could be negative even. Um, let's see which question. Let me look at the question again. Oh, I see what's going on. So again, you have oh, you're talking about the G part. Um, yeah. So okay. So basically, um, notice that if you're saving, if your answers you have to save 130 singular values, since there's going to be uh, uh, since there's going to be say 200 singular values, then you're saving more than half. So k is bigger than n over 2, which is why the compression ratios is screwed up, um, or is not, I should say not screwed up, but is not normal. I'm still here, so you guys can continue to ask questions. I was just muting my mic so that I'm not, um, constantly sitting here breathing. Yeah, Michael. So for 10.7 or 10.8, let me look real quick. Let's see. Consider points stored in the columns of this matrix. These points mostly lie close to a plane through the origin. Yeah. Find the equation of plane, finding the two directions of the most variant. Okay. So if you the two directions of the most variance, that's the two vectors corresponding to the two largest singular values. So you take those two vectors. How do you find a normal vector for a plane if you're given two vectors? Well, you cross those vectors, right? So you take those two vectors, you'd cross them, and then to find the equation for a plane, if you have a point on the plane, you can choose any point that you want that's on the plane. So choose just one of those vectors as point. So take one of those as point, and then you have a normal vector to it that you get by crossing those two vectors. So that gives you the equation to a plane. This is more like it's like Calc 3 review. And then so yeah, using this equation to predict which z value correspond to x equals 10 and y equals minus 3. That's just use that equation you found in part A to see what the corresponding z value would be. So that's how that goes. Same thing for 10.8, I guess. If it's also asking you for the plane. Yeah, find the equation of the plane. It's the same deal. So if you know two vectors that lie in the plane, cross them, and that gives you a normal vector, and then normal vector allows you to write out the equation. Um, 8.3. Oh, it's this question again. Well, so you are. It's up to you to come up with with the example. So 1001. I don't know. Maybe that's. I mean 1001. That's the identity. So yeah, it definitely has eigenvalues 1 and 1. If I would say use another example, right? It's up to you to come up with an example for your matrix that's going to work. For 10.8, use the centered matrix for let's oh yeah, fine. I mean, okay. So that's fine. So you can I see what you mean. I forgot that this problem did that. Um, so yeah, well, I mean, you have this matrix supposed to be representing like a collection of points, right, in space. So then finding the mean of those points in part A, and then centering them about the origin by subtracting the mean, that will give you another list of points. So how many? 8. So you get another list of 8 points. You can put those in a matrix and do the following. Do the remaining analysis. Yeah. So you can. Um, um, you can do that instead. So you can use the modified matrix in parts C and D instead, even though I guess it doesn't explicitly state that, but that's kind of that's the idea. I think there was an example of this done in chapter 10 as well. 13.2 B and C. Oh. um my my advice here is just write out a few. So basically just write out a few of these. So literally for C, do it for k equals 2, 4, 6, 8. For D, do it for k equals 1, 3, 5, 7. You're going to notice something, and then look at how that graph is connected. Right. So look at how the graph's connected. So look how the graph is connected, and then think about what that means for that vertex 5. And that will tell you what's going on. And you don't have to, you're given an intuitive explanation, so you don't have to, there's no like specific terminology that I'm looking for. This is just you trying to reason out why this would be the case. So what do you notice? You're gonna see that pattern when you do those. And then your intuitive explanation should definitely refer to some, the relationship between the pattern you noticed and the way that this graph is connected. So for back to the graph theory issue. So for part C, if you look at the path between 3 and 5, and you say, okay, how many walks of length 2 are there between 3 and 5? And you say, okay, well,
I can go from 3 to 5 and 5 to 3. That's a walk of length 2 between 3 and 5. But notice that the second that you leave 3 in any other direction, right? So 3 is only connected to 2, 4, and 5. So the second you leave 3, well, you have to go back to 3, and then you have to go to 5. So it's that clearly there's nothing you can do there. So then the question is, okay, what about for walks of length 4, right? So you can go back and forth between 3 and 5. If you go from 3 to either 4 or 2, and the way that this graph is, it's not going to matter whether you're going from, to 2 or 4, so let's just pick one. So let's say that you're going from 3 to 2. Well, if you go from 3 to 2 and then back to 3, you can't immediately go to 5, because then you're going to have to go back to 3. So then what are you gonna do here? Well, you can't. If you go down to 4, now you only have one length, one distance 1 left, and that's no good, because if you go back to 3, you still need to get to 5. So that's gonna give you nothing, right? You're not gonna have 1. So what is the problem? It's the way that 5 is tacked on here, right? And the only way to get to it is through 3. It's an issue, right? And it's going to be an issue for even k, period. So then for odd k, you should ask yourself what it is that's going on. So something different happens when you're doing this for odd length walks. Let's see. 1321 part C. Oh, so yeah, no, this one's good. So if you've already made the graph, use Fiedler method. Yeah, explain in terms of the map what the Fiedler method has attempted to do. Well, so if you've done part A and B correctly, then you should just draw the partition of your graph that resulted. Like, so in part B, draw that partition out. Once you've drawn that partition in part B, translate it back into this picture of these like puzzle pieces fitted together. Okay. Or even if you don't want to go through the hassle of trying to draw all that, you should at least take the picture that is, you had to do this for part A anyway. So take the picture that's given to you and label each of those, right? Those become your vertices. Okay, you don't have to redraw this picture with the partition, but when you draw the partition of the graph in part B, match up those vertex numbers with your labeling in your picture, and you'll see, oh, it tried to split these countries while keeping these other countries together, right? So that's, what the Fiedler method is trying to do in general. So the Fiedler method is attempting to minimize the cut, right? So it's trying to minimize the number of edges that would have to be removed from that graph, while keeping the relative size of the two sets that result from that partition being like equal size. So just completely generally being as vague as possible, using that translation of that picture into graph. An edge between two vertices is meant to say that those countries share a border, right? They border each other. And so what the Fiedler method would be attempting to do is minimize the number of edges that have to be removed. So that's minimizing the number of signifiers that two countries share a border, while keeping the two groups of countries roughly the same size. Okay, so specifically you'll be able to see what it is that's going on. Like I said, just label everything in that picture. And when you draw the partition, it will be clear when you think about it for a second what it's attempting to do, how it's attempting to group those countries.
So Lit Mobile just sent me this.
Go beyond.
For the chapter 8, there is a, because I just looked, there is an example in chapter 7 that should work for your 8.3. There's definitely an example that works. because like I said, I literally just looked in the notes and saw it. So, um, yeah, and for exercise 11 in chapter 13, so one you can, as I said, you can actually scale the eigenvectors in question that you use. You're allowed to scale those. You don't have to use them as given because you're interested in that subspace. So you don't have to use those vectors as given. You can modify them if it makes your analysis easier. What do you mean save it as? Oh, what do you mean save it as an info? To save it as an info, you just save it like you would save anything in MATLAB. You just um, um, but if you mean like how do you make? Because I know in chapter um, so in the I'm curious which chapter this is in. There is a now I'm. Oh, are you so if you're talking about using like one of the M files as a function, the main thing to make sure of if you're having issues with that, if that's what you're talking about. So like for instance, if you want to use the function in the MATLAB section in chapter 13, then the main thing to remember when you've made that M file is that you've put it in the right directory. Because if you don't put it in the right directory, then MATLAB's not gonna know what you're referring to when you actually use that. So oh, you mean I see. No, so actually I don't want the raw M file. I don't want that at all. So I want just publish it. So when you go to publish in older versions of MATLAB, it was like a play symbol. I don't know what it is in the most recent versions of MATLAB, but when you go to the publish symbol, by default, I believe MATLAB publishes as HTML. Don't do that because it breaks most of the images. So if you're looking to just publish your MATLAB, there should be a little button underneath publish that's like additional options or whatever, like publishing options or publishing formats. I can't remember what the button actually says, but there's like a little button under the big run like publish button. There's a little button you can press that brings up options. So one of those options is the publishing format. So it's a little drop down menu. Change it from HTML to PDF. That way, when you publish your M file, it will automatically generate a PDF, and you send me that PDF. Or rather, don't send it to me. I mean, upload it to Elms. So yeah, so that's the deal. Oh no, when I was talking about scaling the eigenvector, I wasn't talking about for chapter 8, number 3. Chapter 8, number 3, part. Wait a minute, what are you? Okay, so you got the B part. The A part. The A part. All you have to do is um, basically you just need to come up with a non-regular transition matrix T such that you don't get that convergence. And yeah, that's all you need to do. And like I said, there is an example of this, of the matrix itself in chapter 7. So you can draw what kind of what kind of internet that would correspond to. It's not very complicated. So, I mean, someone was close to it earlier in chat, um, but they missed a very key part. So yeah, if you look in chapter 7, you'll find an example of such a matrix. Also, I mean, I'm sure I haven't tried this, but if you Google like like transition matrices or non-regular matrix, you should be able to find some example of this being discussed. But no, chapter 7 has the example directly. Anyway, so I think time is up. So, like I said, if you have last-minute questions about anything from the projects or the final, you can send me an email, and I'll try to be vigilant since I don't have any duties other than inputting grades, which won't happen. So my plan is to have everything input by the 25th. The absolute cannot miss deadline is the 27th. So so your due date for everything is midnight of the 24th. And if you need a couple extra hours, it's not that big of a deal because I'm not going to look at it immediately, and I won't penalize you for turning in something a few hours late. So that's not like a super strict deadline, but definitely have it done by the evening of have it submitted by the evening of the 25th, because my hope is to try to I have other stuff to grade from other classes too, so my hope is to try to have absolutely everything done by the 25th or 26th, so that I have a day of breathing room. So anyway, that's the deal. So this should be up on YouTube. Of course, those of you that are hearing this, I guess it's kind of pointless to tell you that because you got to see it, but it'll be visible on YouTube if you want to. It's not entirely pointless because if you wanted to go back and re-listen to anything I said about one of these problems, you can do that. It'll be available on YouTube probably in like 2 or 3 hours. But anyway, so that's it for the stream. I'll be around. Let me know if you have any other questions.